Einstein's theory has stood the test of time, but there are still some bold thinkers out there pushing the boundaries. First up, we have modified Newtonian dynamics, or MUND. It tweaks Newton's laws to explain the motion of stars in galaxies without needing dark matter. Sounds pretty wild, right? Next is tensor vector scalar gravity, or TVES. This one combines elements of a MOND and general relativity. It tries to tackle the same galactic mysteries while keeping some of Einstein's ideas. Then there's the Brans-Dicker theory. Named after Karl Brans and Robert Dicker, this theory introduces a variable gravitational constant. It suggests that gravity could change over time or space. Another fascinating contender is the FR gravity, where the F stands for a function of the Ricci scalar r. This theory modifies Einstein's equations to include more complex terms, potentially explaining cosmic acceleration without dark energy. Proposed by Eric Verlinde, emergent gravity, this theory suggests that gravity isn't a fundamental force at all. Instead, it emerges from the information encoded in the fabric of space-time. Despite these fascinating ideas, general relativity remains the reigning champion. But the story doesn't end there. Scientists have also proposed scalar tensor theories, which blend the scalar fields with the tensors of general relativity. Recently, even more complex models incorporating vector fields have been developed. After Einstein's groundbreaking work, theorists sought to refine or even replace general relativity. Some aim to improve earlier theories, while others look to enhance general relativity itself. Various strategies were employed, adding spin to general relativity, combining its metrics with a static space-time model, or introducing additional parameters to offer more flexibility. One intriguing motivation for alternative theories was the desire to eliminate singularities, those mind-bending points where the laws of physics break down. As experimental tests improved, many early theories were discarded. By the 1980s, the increasing precision of these tests had consistently confirmed general relativity, leaving only those theories that included it as a special case. Around the same time, string theory began to gain traction as a promising new framework, though its popularity has waned in recent years. In the mid-1980s, some experiments suggested the existence of additional forces, dubbed the fifth, sixth and seventh forces, acting over short distances. However, subsequent experiments failed to confirm these findings. Today, the motivations for new alternative theories are largely cosmological, aimed at explaining phenomena like inflation, dark matter and dark energy. Let's put these alternative theories into test. First, let's discuss self-consistency among non-metric theories. These theories must eliminate any that allow for tachyons, ghost poles, and higher-order poles, along with those that exhibit problematic behavior at infinity. Among metric theories, self-consistency can be illustrated by several notable failures. For instance, the spin-2 field theory of Fiers and Pauli implies that gravitating bodies move in straight lines, which contradicts the equations of motion insisting that gravity deflects bodies away from straight-line motion. Next, to be considered complete, a theory of gravity must be capable of analyzing the outcome of every experiment of interest. This includes meshing seamlessly with electromagnetism and other physical laws. For example, any theory that cannot predict the movement of planets or the behavior of atomic clocks from first principles is considered incomplete. There are three classic tests, dating back to the early 20th century, to evaluate a theory's ability to handle relativistic effects: gravitational redshift, gravitational lensing, and the anomalous perihelion advance of planets. These tests have consistently aligned with the predictions of general relativity. In 1964, Erwin Shapiro introduced a fourth test, known as the Shapiro delay, which has also become a standard. Einstein's equivalence principle comprises three components: the uniqueness of free fall, Lorentz invariance, and local position invariance. The weak equivalence principle, or the uniqueness of free fall, is satisfied if inertial mass equals gravitational mass. Tests of this principle have become increasingly precise over the decades. Lorentz invariance asserts that the speed of light is constant in the absence of gravitational effects. Local position invariance means that the outcome of any local non-gravitational experiment is independent of where and when it is performed. Schiff's conjecture posits that any complete self-consistent theory of gravity that embodies the weak equivalence principle must also embody Einstein's equivalence principle. Metric theories satisfy this principle, however, very few non-metric theories do. When it comes to strong gravity effects, experimental tests, such as the stability of white dwarfs, the spin-down rate of pulsars, and the orbits of binary pulsars can be used to evaluate alternative theories. General relativity predicts that gravitational waves travel at the speed of light. Many alternative theories suggest that gravitational waves travel faster, potentially breaking causality. However, the multi-messenger detection of the GW170817 event, where light and gravitational waves were measured to travel at the same speed, has excluded many of these modified theories. Cosmological scale tests are just beginning to gain traction. Given the complexity of the theories and limited astronomical data, comparisons involve intricate parameters. For theories aiming to replace dark matter, constraints include the galaxy rotation curve, the Tully-Fisher relation, and gravitational lensing due to galactic clusters. For those targeting inflation, the size of ripples in the cosmic microwave background radiation spectrum is the strictest test. And for theories incorporating or replacing dark energy, supernova brightness results and the age of the universe are key tests. Now that we've explored the rigorous testing of alternative theories to general relativity, it's time to examine some that have fallen short. First, let's consider the stratified theories of Nye, as well as Lee, Lightman, and Nee. These theories are non-starters because they all fail to explain the perihelion advance of Mercury, a critical test for any viable theory of gravity. Next, we have the bimetric theories of Lightman and Lee, Rosen and Rastel. These theories struggle with tests associated with strong gravitational fields, failing to match the predictions of general relativity under intense conditions. Scalar tensor theories include general relativity as a special case, but they only agree with the parametric post-Newtonian values of general relativity when they are nearly identical to it. As experimental tests become more accurate, the deviation of scalar tensor theories from general relativity is being reduced to zero. The same holds true for vector tensor theories. The deviation of these theories from general relativity is also being squashed to zero. Moreover, vector tensor theories are semi-conservative. They have a non-zero value for 2, which can have a measurable effect on Earth's tides. Non-metric theories, such as those proposed by Belinfante and Swihart, often fail to agree with experimental tests of Einstein's equivalence principle. This principle is a cornerstone of general relativity, making any theory that fails to satisfy it highly problematic. So where does this leave us? As of now, no alternative to general relativity has proven to be a valid replacement, except possibly Cartan's theory. However, even this remains highly speculative and has yet to pass all the necessary tests. The situation remained stagnant until cosmological discoveries pushed the development of modern alternatives. These discoveries have reignited the quest for a deeper understanding of gravity, challenging scientists to think outside the box and explore new paradigms.